What does it take to move thousands of tons of material every hour? Entire processing plants, endless conveyor systems, and machines operating at a scale almost impossible to comprehend. From ore beneficiation to final steel products, every step is built for one thing: maximum efficiency at extreme industrial scale. Out on the rugged coastline of Western Australia's Pilbara, where red earth meets the Indian Ocean, the Sino Iron Project rises as a bold vision of industrial scale and global ambition. Developed by CITIC Pacific Mining at Cape Preston, this operation redefines the journey from pit to port. As Australia's largest magnetite mining and processing facility, it transforms vast low-grade resources into high-value concentrate through advanced downstream processing. Backed by CITIC Limited, production began in 2012, marking one of China's most significant resource investments abroad, fueling economic growth, technology exchange, and long-term regional development. The 700 TPH iron ore wash beneficiation plant, developed for CIMEC Mining in Australia, represents a highly engineered wet processing solution designed to upgrade low-grade material into premium products. At the core of the system, the M4500 wash plant performs initial screening and classification at 530 seconds, feeding into a lump ore beneficiation circuit. Here, the AgMax 251 unit delivers intensive scrubbing and dewatering, followed by jig-based gravity separation and dewatering screens to produce a high-grade lump product exceeding 63% Fe. A network of 17 static and radial conveyors ensures efficient material transfer across the plant. In parallel, the fines beneficiation circuit utilizes cyclone technology for slimes removal, followed by spiral separators for gravity concentration, achieving fine product grades above 60% Fe. Integrated water management is handled by 2 of 1,500 units, enabling recycling and sludge control. Overall, the system transforms 17 million tons of overburden into valuable iron ore resources. At the heart of modern industry, steel is not merely manufactured. It is engineered through a tightly orchestrated sequence of thermal, chemical, and mechanical transformations. At Altos Hornos de Mexico, this journey unfolds as a fully integrated process, beginning deep within its own iron ore and coal mines, and culminating in precision-engineered finished products. The cycle initiates with raw material preparation. Iron ore arrives as slurry through an extensive pipeline, where it undergoes filtration before entering pelletizing discs. Mixed with binders and fired at approximately 300 degrees C, the material is transformed into hardened pellets optimized for reduction. In parallel, metallurgical coal is processed in coke ovens, sealed, refractory-lined chambers where, over 18 hours of controlled heating, it is converted into coke, the primary fuel for iron making. Byproducts such as coke oven gas are recovered and reused, enhancing overall energy efficiency. Supplementing these inputs is sinter, a recycled composite of fine iron particles blended with fluxes such as limestone and dolomite. Once prepared, pellets, sinter, coke, and fluxes are charged into towering blast furnaces exceeding 160 feet in height. Within this high-temperature environment, reaching up to 650 degrees C, iron oxides are chemically reduced, producing molten pig iron. The liquid metal collects in the furnace hearth and is periodically tapped into torpedo cars for transport. Before advancing, the pig iron undergoes desulfurization, where reagents such as magnesium and calcium carbide remove impurities. The next phase converts this iron into steel through 2 primary routes. In the basic oxygen furnace, BOF, molten iron is combined with scrap and refined by injecting oxygen, argon, and nitrogen, reducing carbon content and impurities within approximately 45 minutes. Alternatively, electric arc furnaces, EAF, utilize high-energy graphite electrodes to melt scrap and iron units, offering flexibility and efficiency in steel production. The resulting liquid steel is then treated in secondary metallurgy stations, where its chemical composition and temperature are precisely adjusted. Advanced processes, such as vacuum degassing, further enhance purity by removing dissolved gases. From there, the steel enters continuous casting machines, solidifying into slabs as it passes through water-cooled rollers before being cut to size. These slabs form the backbone of downstream processing. In hot rolling mills, reheated to over 300 degrees C, they are reduced into plates or coils through successive rolling stands. Cold rolling further refines thickness and improves mechanical properties, followed by annealing and surface finishing processes such as tempering and skin pass rolling. From structural beams to automotive-grade sheet, AMSA's vertically integrated system delivers steel products that meet rigorous global standards, an industrial ecosystem where raw earth is transformed into the structural framework of modern civilization. In the unforgiving depths of the world's mines and the relentless forces of offshore environments, reliability is not optional, it is engineered. Since 1921, Hagi steel wire rope has stood at the forefront of this discipline, evolving from a supplier to South Africa's gold mining sector into a globally recognized authority in high-performance rope systems. As the only fully integrated wire rope manufacturer in the Southern Hemisphere, Hagi controls every stage of production, from high-carbon rod drawing to final rope construction. This vertical integration ensures unmatched consistency, enabling the production of bright and galvanized high-tensile strands across a wide spectrum of configurations, including 6- and 8-strand ropes, rotation-resistant designs, and compacted triangular constructions. Its legacy is deeply rooted in mining innovation. Hagi's mine hoist ropes operate in some of the deepest shafts on Earth, extending beyond 3,000 meters, while continuous engineering advancements have increased fatigue life from 12,000 to an impressive 99,000 cycles. In surface mining, specialized dump ropes are designed for durability and rapid replacement, minimizing costly downtime. Beyond mining, Häggi plays a critical role in offshore industries, supplying anchor lines engineered to withstand extreme marine conditions. Backed by rigorous in-house testing, including SANUS-approved brake testing, every rope meets stringent international standards. After more than a century, the Häggi name remains synonymous with precision, safety, and enduring performance. The Excavator Group has strategically expanded its rental fleet with the addition of 12 identical heavy-duty steel lifting slings, each measuring 61 meters in length and 0.36 meters in diameter. Engineered for demanding industrial applications, these slings are purpose-built to handle extreme loads in sectors such as offshore construction, heavy infrastructure, and energy installation. Each sling represents a precise integration of traditional craftsmanship and advanced machining technology. High-tensile steel wires are carefully selected, treated, and assembled into robust cable structures capable of withstanding immense mechanical stress, dynamic loading conditions, and harsh environmental exposure. The fabrication process emphasizes structural integrity, fatigue resistance, and long-term durability, critical parameters in heavy lifting operations. From initial engineering design through to final production, the manufacturing workflow is tightly controlled. The supply chain plays a pivotal role, with raw materials sourced from specialized producers in Asia and delivered under a just-in-time logistics model. This approach ensures optimal inventory efficiency while maintaining strict adherence to production schedules and quality standards. The result is a series of industrial-grade lifting slings that meet rigorous performance criteria and certification requirements. These components are not merely tools, but essential load-bearing systems designed for reliability in mission-critical operations. By expanding its fleet with these high-capacity slings, Excavator Group reinforces its position as a key provider of engineered lifting solutions for large-scale, high-risk industrial environments. In offshore engineering, scale often defines possibility. In May 2013, the Excavator Group set a remarkable benchmark by producing two cable-laid slings, each stretching an extraordinary 280 meters, believed to be the longest of their kind ever manufactured. Each sling, weighing 63 metric tons, was meticulously terminated with hand-spliced soft eyes, ensuring both flexibility and structural integrity under extreme loads. Designed for subsea installation, these colossal assemblies were deployed by Saipem at the Asgard field in the Norwegian Sea. More than sheer size, these slings represent precision craftsmanship at an unprecedented scale, where engineering accuracy, material performance, and offshore reliability converge to enable complex deepwater operations. When the world's heaviest loads must move across oceans, into the depths, or high above the horizon, precision and trust become everything. United Offshore Services operates at this extreme edge, delivering lifting solutions engineered to perform where failure is not an option. From fine 6mm ropes to massive 500mm diameters, UOS provides tailored systems built on premium-grade steel and advanced fabrication. At the core of its capability lies a unique grommet production system, capable of handling components up to 150 tons and 300 meters in circumference, ensuring exact length tolerances and structural integrity. Every sling and rope is rigorously inspected, tested, and certified, supported by high-capacity testing machines exceeding 300 tons of traction force. Beyond manufacturing, UOS integrates logistics, maintenance, and inspection into a seamless lifecycle solution, cleaning, protecting, and storing equipment under controlled conditions for rapid deployment. In offshore and marine operations, where conditions are relentless, it delivers not just equipment, but engineered certainty. Every steel wire rope begins with a single filament, drawn, refined, and engineered for strength. In this transformation, raw steel rod is pulled through precision dies, reducing diameter while enhancing tensile properties. Individual wires are then twisted into strands, each carefully aligned to balance flexibility and load capacity. These strands converge in the closing stage, where they are helically wound into a finished rope. The result is a highly engineered structure designed to endure extreme forces, an essential component in lifting, mining, and heavy industrial systems where failure is never an option. Engineered for precision and clarity, the Performa 043mm sight tube for Brazil reflects advanced manufacturing excellence. From CNC machining to optical assembly and finishing, each unit is crafted to ensure durability, accuracy, and reliable performance in industrial inspection environments. From the precision floors of advanced manufacturing plants, steel cables begin a journey that extends far beyond the factory gates. Forged through drawing, stranding, and closing processes, each rope is engineered with exacting control, designed not just to perform, but to endure. From there, these cables travel across continents, finding purpose in some of the world's most demanding environments. They carry cable cars over alpine peaks, anchor massive bridges against wind and time, and support the sweeping roofs of modern stadiums and glass facades. In ports, offshore platforms, and urban infrastructure, they quietly sustain motion and stability. What begins as raw steel in a factory evolves into a global network of strength linking Indus. At Bardon Hill Quarry in the UK, one of the nation's oldest continuously operating sites, a new chapter in material transport is unfolding. To support quarry expansion and restoration, Doppelmayr Transport Technology deployed the RopeCon system, a hybrid solution that merges conveyor efficiency with ropeway flexibility. Engineered to move 1,000 tons of overburden per hour across steep terrain, the system spans 850 meters with inclinations reaching -33 degrees. Pre-crushed material is fed into the line, where a regenerative drive converts gravitational energy into usable power, significantly reducing overall energy consumption. Beyond performance, the system minimizes environmental impact, cutting CO2 emissions compared to traditional haulage. With adjustable discharge heights, dual unloading points, and integrated inspection access, RopeCon transforms quarry logistics into a cleaner, more intelligent operation. High above the narrow alpine terrain of the Schilthornbahn project, where every meter of space is hard-won, installation becomes a test of precision and coordination. At Tower 3, Garaventus' team undertakes the complex assembly of the rope saddle, delivered in 2 sections via material ropeways, navigating steep terrain from Stechelberg to Murren before reaching the site. With no workable space at the base, the operation shifts skyward. The 2 halves are aligned, bolted together, and carefully lifted using synchronized cable winches. Suspended mid-air, the structure must be guided, braked, and positioned simultaneously, every movement calculated, every force controlled. In this environment, even minor misalignment carries risk. Yet through disciplined execution and engineered systems, the rope saddles are secured, marking a critical milestone as the project advances toward completion. From a technical standpoint, Besav Kablo operates a tightly controlled, vertically integrated cable manufacturing system. Copper and aluminum are first processed into wire rod, then drawn through multi-stage dies to achieve precise diameters and mechanical properties. Conductors are stranded to optimize flexibility and current carrying capacity before entering extrusion lines, where insulation and sheath layers are applied under controlled temperature and pressure conditions. Advanced compounds ensure dielectric strength, thermal resistance, and long-term durability. Inline testing, spark testing, dimensional control, and surface inspection guarantees defect-free production. With a monthly capacity of 500 tons, the system maintains consistent output while meeting international standards for electrical performance, mechanical integrity, and operational reliability across demanding infrastructure applications. From molten metal to precision safety component, a brake disc is shaped through a controlled casting and finishing sequence. Inside the pouring furnace, iron is melted and prepared for casting, while the core shop produces internal sand cores that define ventilation channels. In the molding area, these cores are placed into sand molds before molten metal is poured to form the disc. Once cooled, raw castings enter the drum and finishing area, where machining operations refine surfaces and ensure dimensional accuracy. Every disc then undergoes strict quality control, checking balance, hardness, and structural integrity, before moving to the warehouse, ready for distribution and installation in demanding braking systems. In the world of mechanical engineering, a seemingly simple hammer is the result of a tightly controlled manufacturing process, where raw materials are transformed into durable, long-lasting tools. The process begins with carbon steel or alloy steel, cut to standard dimensions before being placed in a furnace. Here, the steel billet is heated to a high temperature, reaching an ideal ductile state for forging. Under strong pressure from a power hammer or stamping machine, the red-hot metal is shaped into a hammerhead with a tightly compressed grain structure, increasing its mechanical strength. After forging, the product undergoes machining. Surfaces are turned, milled, and ground to achieve precise dimensions and a high level of finish. The handle mounting hole is carefully machined to ensure a tight fit and safe use. Next is heat treatment, a crucial step in determining the hammer's performance. The hammerhead is hardened to increase wear resistance, then tempered to reduce brittleness and improve impact toughness. The balance between hardness and ductility is the core element of a quality product. After assembly, laser engraving precisely prints the brand and specifications onto the surface, ensuring the durability of the markings over time. Each hammer undergoes rigorous quality control testing, ensuring its load-bearing capacity and safety before reaching the user, a small tool, yet possessing the power of modern metallurgy. Finally, the product undergoes further quality checks before being carefully packaged, ready to leave the production line and enter the harsh working environment where performance and reliability are vital. In high-precision valve manufacturing, 8RRI Machining's top-entry three-way ball valve reflects advanced CNC machining and surface finishing expertise. Components undergo multi-axis milling, followed by grinding and polishing to achieve tight tolerances and smooth sealing surfaces. Industrial machines refine metal interfaces to reduce friction and ensure leak-proof performance under pressure. The result is a robust valve system engineered for durability, flow control accuracy, and long-term reliability in industrial environments. An excavator bucket is not simply fabricated. It is engineered through a sequence of tightly controlled processes where material quality and welding precision define its lifespan. Not as a simple steel attachment, but as a precisely engineered tool built to endure relentless force. Every stage is governed by discipline, where design intent is translated into physical strength. The journey advances through high-precision cutting, where thick steel plates are shaped with accuracy to match demanding specifications. Each segment is then bent under controlled force, forming the curvature essential for efficient material penetration. Dimensional inspections follow, ensuring every contour aligns perfectly with engineering drawings. Assembly begins in the fit-up stage, where components are carefully positioned to establish structural integrity before welding. This alignment is critical. Any deviation compromises performance under load. Welding then defines the bucket's durability, executed with controlled heat input and high-strength consumables. Each seam is built to resist abrasion, shock, and cyclic stress in harsh environments. Surface preparation through shot blasting strips away impurities, revealing clean steel ready for protection. The installation of teeth and adapters follows, where pins are driven and locked into place, forming the cutting edge that engages directly with the earth. A final coating seals the structure against corrosion. What emerges is not just a bucket, but a hardened extension of the machine, engineered for endurance, precision, and the unforgiving realities of excavation. Within the precision-driven environment of advanced valve manufacturing, every component is engineered to withstand extreme pressure, temperature, and corrosion. At Mechanica Gervasoni, the process begins with the meticulous machining of valve balls, prepared to exact tolerances before entering the critical weld overlay phase. Using MIG, TIG, and SAW processes across 16 certified stations under standards, specialized alloys duplex, and super duplex are applied. Supported by 6 FANUC robotic systems, the overlay is executed with exceptional consistency, forming a corrosion-resistant and wear-resistant surface layer. Following overlay, precision machining restores dimensional accuracy, preparing the surface for advanced coating technologies. High-velocity oxygen fuel processes apply tungsten or chromium carbide coatings, dramatically enhancing hardness and erosion resistance. Subsequent grinding refines the surface, while lapping ensures perfect sealing between ball and seats. Quality assurance is deeply embedded throughout. Each component is fully traceable, with heat numbers, drawings, and serial identifiers recorded. Non-destructive testing, including dye penetrant inspection, ultrasonic examination, and thickness verification, confirms structural integrity. PMI analysis guarantees material composition, while metallographic studies, hardness, and bond tests validate performance. The result is not merely a valve component, but a precision-engineered solution built for reliability in the most demanding industrial environments. In high-performance transmission systems, a bevel gear is never just machined. It is generated with calculated precision, where every micron defines load distribution, noise, and longevity. The production of a dry-cutting bevel gear M8Z33 reflects a modern shift toward efficiency, thermal control, and tool optimization. The process begins with a forged steel blank, selected for its strength and grain integrity. After normalization, the blank undergoes turning to establish critical reference surfaces, bore, pitch cone, and face geometry, forming the foundation for accurate tooth generation. At the core lies dry cutting, where advanced CNC bevel gear machines use carbide tools to generate tooth profiles without coolant. This approach eliminates thermal shock, while maintaining high cutting speeds. The cutter, rotating continuously, engages the stationary workpiece in a controlled motion, shaping each tooth with precise geometry and contact patterns. Chips are evacuated efficiently, and tool coatings ensure durability under elevated temperatures. Process control is critical. Machine alignment, cutter condition, and real-time measurement govern tooth thickness, runout, and surface finish. Unlike conventional wet machining, dry cutting demands exact parameter calibration to avoid tool wear and maintain dimensional stability. Following cutting, gears may undergo heat treatment to enhance hardness and fatigue resistance, then return for finishing operations such as grinding or lapping to refine contact surfaces. Final inspection validates every parameter, from geometry to surface integrity, ensuring the gear meets stringent transmission requirements. What emerges is a precisely engineered component, optimized for efficiency, durability, and silent performance in demanding mechanical systems. Before a circular saw blade ever engages with wood, metal, or composite, it must first be engineered to endure the extreme conditions it will generate: heat buildup, high rotational forces, and continuous friction. At Gudo, this transformation unfolds through a precisely controlled manufacturing chain, where every stage is calibrated to deliver structural integrity and cutting accuracy. Production begins with premium-grade raw steel, selected for its chemical composition and consistency. Through rolling, the material is refined to a uniform thickness while optimizing grain alignment, an essential factor for strength and fatigue resistance. Laser cutting then shapes the blade's outer diameter and tooth geometry with exceptional precision, ensuring repeatable accuracy across every unit. The blade is then subjected to heat treatment, where carefully controlled thermal cycles alter its microstructure. This step delivers the hardness required for wear resistance while maintaining sufficient elasticity to absorb dynamic stresses without cracking. Following this, milling operations define functional surfaces, and multiple grinding and polishing stages refine flatness, edge quality, and surface finish. Oiling and demagnetization stabilize the blade, preventing contamination and unwanted particle adhesion. Bore inspection ensures precise mounting tolerances, followed by a thorough washing process to eliminate residues before assembly continues. For carbide-tipped blades, brazing securely bonds cutting inserts to the steel body, forming a highly wear-resistant cutting edge. Surface preparation through sandblasting enhances coating adhesion, while tensioning introduces controlled internal stresses that stabilize the blade during high-speed rotation. Straightening corrects even minimal deformation, and additional grinding and polishing ensure final dimensional accuracy. Pinholes are precisely added for secure installation. Advanced coatings are then applied to reduce friction, limit heat generation, and protect against corrosion. Marking and printing embed technical specifications and traceability directly onto the blade surface. Finally, rigorous end control verifies balance, geometry, hardness, and overall performance. The result is a precision-engineered circular saw blade built not just to cut, but to deliver consistent, reliable performance under the most demanding industrial conditions. High above the ground, where precision meets risk, helicopter tree sawing transforms vegetation management into a highly specialized aerial operation. Suspended beneath an MD-500 helicopter, a multi-blade cutting system becomes an extension of the aircraft, demanding absolute coordination between pilot skill, machine control, and environmental awareness. The system itself is deceptively simple in concept, yet complex in execution. A vertical assembly of circular saw blades is mounted on a lightweight aluminum boom, hanging securely below the helicopter. Powered by an independent gas-driven motor, the blades reach high rotational speeds, ready to slice through dense branches with clean, controlled cuts. From the cockpit, the pilot maintains full operational control, engaging the saw, managing RPM, and adjusting orientation relative to the flight path. What defines this operation is not just the machinery, but the precision flying required to execute it. The pilot must simultaneously maintain stable hover or controlled lateral movement while aligning the saw with targeted branches, often in close proximity to power lines. Every movement is calculated, as spatial awareness becomes critical to avoid hazards both in the air and on the ground. Equally important is the coordination between pilot and ground support, forming a synchronized system that ensures safety and efficiency. Operating under demanding schedules, crews balance intense work cycles with recovery periods, reflecting the physical and mental demands of the job. The result is a method of tree management that is fast, efficient, and remarkably precise, where aviation expertise and mechanical engineering converge to reshape landscapes from above. In modern fabrication, precision and efficiency converge in the industrial-grade fiber laser system equipped with a hydraulic lifting platform. Designed for advanced sheet metal processing, the machine performs high-accuracy bevel cutting, creating angled edges essential for welding preparation and structural assembly. The hydraulic table enables smooth lifting and rapid exchange of workpieces, minimizing downtime and maintaining continuous production flow. Integrated fireproof and thermal insulation technologies ensure safe operation under high-energy laser conditions, protecting both equipment and operators. Together, these systems deliver clean cuts, reduced post-processing, and optimize productivity in demanding industrial environments. Inside a precisely orchestrated industrial environment, fiber drums emerge as engineered packaging solutions designed to safeguard powders, pastes, and semi-liquid materials across demanding sectors like chemicals and pharmaceuticals. Strength begins with raw inputs, massive coils of paper and industrial-grade adhesives, staged and prepared for continuous production. A wide paper web is fed into forming machinery, where adhesive is applied and the material is tightly wound into multi-layered cylinders. Layer by layer, often reaching up to 7 plies, the structure gains remarkable compressive strength, resulting in long, rigid tubes. These cylinders are then conveyed along elevated tracks, allowing controlled drying that stabilizes the bonded structure. In parallel, steel components are fabricated. Rims are cut with precision, welded into continuous structures, and finished to ensure dimensional accuracy. Once the paper cylinders return to the line, they are cut to size, and a reinforced base is mechanically crimped into place, embedding steel into fiber to create a robust hybrid interface. The top ring is then installed, forming a secure closure system. Advanced inspection systems verify cleanliness and structural integrity, critical for pharmaceutical compliance. The final product stands as a fusion of material science and process control, lightweight, durable, and engineered for protection at scale. In precision motor manufacturing, the Talon starter motor armature winding machine is engineered for high-efficiency coil formation and repeatable accuracy. Using PLC-controlled mechanisms, the machine performs wire straightening, enamel removal, cutting, and coil forming in a continuous cycle. Designed for copper wire diameters up to 4.0 millimeters, it delivers high-speed production, low defect rates, and stable winding structures, forming the foundation of reliable starter motor performance. Inside every reliable engine start lies a precisely engineered armature, where electrical energy is transformed into motion within milliseconds. In modern manufacturing, the starter motor armature production line for hairpin motors represents a fully integrated, high-precision system tailored for automotive and new energy applications. At its core, the armature consists of laminated iron cores mounted on a shaft, copper windings formed in hairpin geometry, and a commutator for current distribution. The process begins with insulation paper insertion, ensuring electrical isolation within the slots. This is followed by automated coil insertion, where preformed conductors are placed with exact positional accuracy to maintain electromagnetic balance. Next, the commutator is pressed onto the shaft under controlled force, guaranteeing alignment and mechanical integrity. Spot welding then establishes robust electrical connections between windings and commutator segments, minimizing resistance and ensuring durability under repeated thermal and mechanical stress. Each stage is synchronized through automated control systems, delivering consistent quality, high throughput, and tight tolerances. The result is a critical component engineered for efficiency, reliability, and performance in modern vehicles. In the precision world of metal forming, the 6-block bull block wire drawing machine transforms raw rod into high-strength wire. Through sequential drawing dies, each block reduces diameter while maintaining tensile integrity, supported by controlled lubrication and cooling, delivering consistent, high-quality wire for demanding industrial applications. Beneath the surface of modern infrastructure, an unseen network carries water, sustains agriculture, and supports entire cities. At Diamond Plastics, that hidden system begins its life in a highly engineered production environment, where raw materials are transformed into some of the largest PVC pipes ever manufactured, reaching diameters of up to 60 inches. These pipes are designed for water, sewer, and industrial applications, where long-term reliability is critical. The process starts with carefully formulated raw materials. PVC resin is blended with stabilizers, lubricants, and performance additives, each precisely measured to meet strict application standards. These ingredients are conveyed into sophisticated mixing systems, where controlled heat and mechanical agitation transform them into a uniform, pliable compound suitable for extrusion. Depending on the pipe specification, multiple formulations may be prepared simultaneously to ensure consistent quality and performance. Inside the extrusion line, the compound enters a heated barrel equipped with precision screws. As the material softens under heat and pressure, it is forced through a die system maintained at temperatures exceeding 300 degrees Fahrenheit. A sizing sleeve immediately defines the pipe's external diameter, while puller speed carefully controls wall thickness, ensuring that each pipe meets exacting industry standards. Internal air pressure stabilizes the newly formed pipe as it exits the die, maintaining a true circular shape. The pipe then passes through a series of cooling tanks, where chilled, recycled water solidifies its structure while preserving dimensional accuracy. Once cooled, each pipe is printed with traceable production information and cut to standardized lengths using synchronized carbide saws. For certain products, bevels are applied to the spigot ends to facilitate connections in the field. This process demonstrates how advanced engineering, strict quality control, and innovative manufacturing come together to produce PVC pipes that stand the test of time, safeguarding essential services while minimizing environmental impact. A critical stage follows, the belling process. One end of the pipe is reheated and expanded over a mandrel to form a socket that integrates a rubber gasket, creating a tight, leak-resistant joint. Pressure-rated pipes undergo hydrostatic testing, where sections are filled with water and subjected to extreme internal pressures to confirm structural integrity. Additional quality checks include impact, stiffness, flattening, and burst tests, verifying performance under real-world conditions. Finally, the pipes are bundled, tracked, and transported across North America for installation. Every step, from raw material blending to hydro testing, reflects Diamond Plastics' commitment to reliability and precision. What emerges is more than a product. It is a long-term infrastructure solution, engineered to protect water resources and support modern communities for generations. The 1000L extrusion blow molding machine is a versatile solution for producing high-quality plastic water tanks and road barriers. Designed to handle capacities ranging from 300L to 1000L, it supports multi-layer extrusion from 1 up to 6 layers, allowing manufacturers to optimize strength, durability, and material efficiency. The machine operates by extruding molten plastic through a die to form a hollow parison which is then clamped and inflated within a mold to take its final shape. Multi-layer extrusion enables the combination of different materials or recycled content for enhanced performance, UV resistance, and chemical stability. Ideal for municipal, agricultural, and industrial applications, this machine ensures uniform wall thickness, precise dimensions, and smooth surface finish for every tank or barrier produced. With advanced controls and hydraulic systems, it offers consistent production, reduced waste, and easy operation. The machine's design supports high efficiency, making it suitable for continuous production lines of water storage tanks, road safety barriers, and other large hollow plastic products.